Today, we're walking through anti-patterns and patterns clearly. And next week, or 2 weeks from now, sorry, availability and the scalability cube. And you can read the rest of them as we go. But we're hitting a little more of the technical side, really in sequence from what we talked about last week. So we're excited to be rolling through this with you. We do want to encourage you guys, if you have not, to subscribe to our YouTube channel. That's where we're posting all of these. All the videos that we've done from the previous webinars are out there and available to you. Encourage your colleagues to look at it too. These are available for free. We want people to take advantage of the information that we can share. So if you haven't subscribed, we encourage you to do it. Today is all about anti-patterns and the correct patterns, how you adjust and correct those things that are not something that is cohesive or beneficial to your software design. Lots of them that we're going to go through. We may not get to all of these. We do want to get to a few of them in particular simply because they're very, very common and very popular and very powerful when you begin to use them. Common questions when you're splitting a service. That's the first piece we want to walk through. How granular do you get? We call them microservices. In some cases, that may be a misnomer. They're too small. They serve too small a purpose, and you have more services than would be necessary. How many swim lanes need to be split out? There, you're looking at the ability to fault isolate. There's a couple of patterns we'll walk through specifically on that topic alone. And what services should or could be grouped together. So you've got a team, a cohesive 9 to 12 person team that maintains a functional process that may or may not be one or two services, but could those services be combined logically within the team? You want to make sure that anytime a new service call results in a series, you're going to inherit higher failure rate and lower availability simply because of the math we walked through on our last webinar. So those are not things that you want to do. Likewise, if you have to add in more infrastructure because you've broken services out, you're adding cost and lowering your overall margin without adding any real new functionality. You've just broken it apart. So those are also not a great idea. We want to walk through the scale cube and how we look at the y-axis splits on two areas. We're going to look at how often you update the software and the amount of functionality that's in each individual piece of software. The size of the bubble indicates the overall size of the code base as a percentage. So you've got a monolith, very low rate of change. There's a large percent of the code base, and it's got a very diverse bit of functionality in it, a lot of different functions all in one piece of software. That contrast then with microservices where you are changing it rapidly. You're changing it perhaps even weekly, maybe even more frequently than that. But the functionality is very laser focused. It is targeted for one specific purpose, and that is all you do. When you need to change that, it's relatively easy because you're not impacting any other services around it. There's not a lot of interaction except through the interface layer. So you've got a low risk of services down in the monolith, and you've got higher risk services where you've got a risk of an outage, you've got a risk of change impact. That's where you start to break them apart. Some other elements that you walk through is what's the overall throughput? We mentioned already the frequency of change, but how much is it being reused? How much is that code being reused? What's your overall team size? If you need a team of 30 people to maintain a monolith, that's double at least the size we would expect. That's a target to be able to break things apart and start to get to a team size that can be autonomous and maintain itself and have much higher throughput of the changes. You also look at the criticality for the business and what happens if we have a failure. The availability and fault tolerance contributes to when you break out a service as well. You don't want to break it into too small chunks for the same reason. You end up inheriting additional cost. So there may be a cost element that you want to consider, and certainly scalability, not only of the software, but of the data. When you get data, that a single database that is way too big, it's time to shard that. And that, in that case, for disaster recovery, you should try and put it into a different region or a different, at least a different availability zone, and spread the data across multiple places. That means you also should begin to look at splitting those services so you have them serving in the same place. So let's walk through a decision tree, and then I'll take some input and feedback from you guys. Does this service have a high rate of change? That's probably the primary thing we would always talk about. If not, look to see if there's a business critical service, something that is critical to what you're running? If it is, does it have high risk of failure? Based on the nature of what code is in there, does it fail a lot? If yes, split it until you can get your risk levels for failure down to a place where it's acceptable. If not, then you look at the high volume usage. Based on other services, does this get a lot of attention, a lot of traffic? If not, you need a specialized skill set. Is this something that is a particular business domain or a technical domain that's necessary? If not, is it reused in a number of places? Is the data required to operate it, is it scaling rapidly? Is it growing quickly? If it is, split along the z-axis. Break those data pieces into two, split the services and place those services in the place where the data resides. If not, you probably can leave that as a monolith. It has a low rate of change. It's not business critical. It isn't a specific skill set. So you've answered no to all these questions. That's likely something, even if it's significant and large, because of all those factors, leave it as a monolith. It's okay. Let's answer those questions in another way, though. If it does have a high rate of change, if we segment it, is it going to be cost prohibitive to do so? If yes, then you got to look at your data and you're back on the right side of the equation. If no, is it dependent on any other services for its function? Does it have a, not necessarily call in series, but does it make a dedicated and necessary call to be able to fulfill itself? Do other functions need to stop if that's unavailable? It's looking towards a circuit breaker where you know that the function is unavailable, so you build resilience into your code. At that point, you look at splitting it off by itself. If it is, if other functions do need to stop, then split it with dependent services as a group so that they function together and you reduce your overall risk of non-availability. Now, if it is dependent on other services, can it be eliminated? Can you combine those pieces of code together so you don't have the service to service calls? If not, split them as a group. If yes, then split it off individually and try and isolate, build some fault isolation around it. You can also try and combine those pieces of code. Now, we didn't have the yeses to any of these questions. If you've got high volume, you've got a specialized skill set or high reuse, then you come over to answer about cost prohibitive and proceed down the left side of the slide. Have any of you guys walked through and split services and asked some of these same questions in your organizations or your environments? You can answer within the chat. David, you want to share with us what your experience was?
Yeah, I mean, we did it actually with a partnership with y'all earlier, and we're continuing to do that, as we think about new services that we're building out. But it is very much, first it started going down the right side, right, of this model, thinking about the services that we have, and most of those are not high risk, so they kind of went into that no column of high volume, right, or specific skill sets. And it has been an ongoing process of breaking that off from a monolith into microservices where it makes sense. But, we are definitely toying around with the concept of how small do you get with these? How can we make sure that we're, thinking about the isolation and the data that supports those services, that they're centralized in a way that we can scale up or have them independently fail and not affect, the broader system. So all those things have been valuable conversations to be had. And I think this has been a good model for us to kind of assess when and how to do it.
Thanks.
One more thing I'd like to add on David's scenario. They were a unique client of ours where they started as a B2C company, and then they quickly found a bigger market opportunity in a B2B with similar functionality where they kind of white labeled the capabilities, but provided some additional enterprise management capabilities. But the two companies that they actually split into two companies, but were managed by the same parent company. So they actually had the incentive to stay in touch. So they forked the code base, split up the teams, and then because they were had the same ownership structure, they realized these code bases diverged, and over time it was better to reconverge some elements. So they had more incentives to actually deal with this and split up and make more of a platform architecture versus a lot of other clients that we see where they have done an acquisition, very different code base, and they're trying to create a platform. So they've deferred and keep pushing it down the road the need to split off services and create more of a platform architecture. So it was very interesting client for us. I'm curious for the rest of you, what led you to go down the path of splitting a service? Was it due to an acquisition and you wanted to create more of a platform, or you just had an old monolith you needed to split? So I'm looking at Nicholas here.
Yeah, good questions, Nick. I'm curious if you would be willing to share some of your experience with us verbally.
Yeah, sure. Actually, it's interesting. I think this was many years ago where you guys came in and actually helped us. This is like 2017 or so, and we had a global website, and it was a monolith. And I think that was probably so we knew the monolith was a problem, and we had all these back-end dependencies. So we're a very traditional enterprise. A lot of the functionality of the site was based on directly interacting with ERP or those kind of things. So it was all about how do we split, with some of the splitting was really how can we split the site to be able to be less impacted by downtime in those back end systems. So split all the services maybe that I'm speaking to an ERP versus things that are speaking to a reporting system and so on. And then obviously bring in caching so that you can have this have your service be highly available, or have the website have partial degradation instead of full degradation on any of the outages in the backend system. So but obviously that would just be the initial to just get to that 24/7 point, or the better, or to be sort of partially available at least through all periods of all of that downtime. But this certainly kind of takes it to the next level where you can really start getting more and more fine grained. And how do you ask those? I think this is something that we could never really answer in our mind. Once we do that split, how do we systematically then go through the rest of the site and identify when we need to start splitting more and more and more, and maybe even move functionality around out of maybe where it was in back end systems into different systems. So, yeah.
Good, thank you.
I just want to add one more comment, Doug, before you jump into the patterns and anti-patterns. So what Doug's going to walk through are the right things to do and the wrong things to do. And a lot of them are going to suggest how you need to split off a service and what we call these functional splits. So we're not going to explain where in your architecture to split. That's really where domain-driven design comes into play. What this focus on is around identifying risks around how you split up your architecture and the math and the risks behind that. So, and the general pattern to remediate these. So if you're worried about how am I going to do this in practice, we're not going to answer that specifically yet. It's more around this is the pattern you need to move to, and this is the business reasons and justifications why you need to make a split in a particular way. So, all right, just want to set that up, Doug, before you
Good, thanks.
jump in.
We always address these back to the scale cube. X is scaling out horizontally, so you add in additional servers, you add in additional services. What this is doing, we're looking at it maintains a monolith, which, as I said, a monolith, when it gets to a certain size, is just fine. It's a piece of software that isn't regularly changed and doesn't have a lot of impact. There are two areas here when we're splitting services. Those address the y-axis. And our last one then, splitting along the z-axis, is where you take the monolith, split the database monolith, and geographically disperse it if you can. Service call in series is our first one that's an anti-pattern itself. We call this a Christmas lights because anybody who's plugged in the current Christmas lights knows that when one of those lights goes out, the whole string goes down. Your availability is a function of the number of services multiplied. So if this is 99.9, this is the math we walked through with you guys last week or 2 weeks ago. Your availability is a multiple and a lower multiple based on the number of services you have that are in series with one another. So definitely not a place that we want to see things happen. A remedy for that is to make those calls asynchronously. So the services, rather than calling one another in series, the services address a message bus. Each of these additional services publish to and subscribe to that message bus or multiple buses to make sure that the synchronous communication is no longer a problem for you. You can also have a service call individual library. So service B has a number of functions, build that into a library, C and D, and that service A can then, rather than calling the services in series, can call the libraries within its own environment directly. There's the bad Christmas lights.
Let me just pause there. If we go back to the libraries,
Sure.
in the past, when we would teach the class, a lot of folks would not quite embrace why libraries are important. So I'm going to ask the audience, and this is the lessons from the last class, why are libraries better than the other approach? All right, no answers. Well, the key is, remember, if the library is on that particular compute, it's just fewer things that can break in that component-to-component communications. Yep, exactly. Only jump the network if you need. That's exactly right. You're avoiding any call from one particular machine to another particular machine. So
Good. Thank you, Nicholas. Fuses, there's a couple of them that we'll talk through. The service fuse is where two services call directly to service C. So if service C is down, neither one of these services can complete their function. So you've got a fuse. When the fuse is out, all of the lights in the house go out. Direct services should never share a common service. A correction for that, obviously, is to split the services, split service C so that each individual service can call it directly and distinctly without any parts of the fuse left in place. For the same reason, you can turn all of the functions in C into a library, so you can, at that point, avoid the cross-network calls altogether. Data fuses exist as well. This is actually one of the examples that we walked through in our discussion last week or 2 weeks ago, where there was a database that was called by multiple services and it became a fuse. The solution is remarkably similar. You split that data and build a process for replication or eventual consistency of the data across, or you make the individual data stores distinct for the services. There's another approach that's addressed here where services from A and B are combined and then they don't have a data fuse. They're both conferring directly to the same database. You can also build in a write and a read replica with eventual consistency with replication from the read replica so that it reads only from one database and you reduce the load dramatically on the write database that's necessary to manage the transactions. There we go. And eventually you're going to have consistent replication. It's not immediate. That's purely dependent upon the nature of the replication and the amount of data you're trying to move. The other is you can take the functions and split the data distinctly. So the add to cart, in this case, the data is split between what's needed between D and E. Or you can have the data managed within the browser. So it's going to take the add to cart elements and route it over to the checkout itself. Or you can move the cart object asynchronously between those two databases, and within a very short period of time, you've got a replicated set of data so the checkout can proceed normally. Comments or thoughts on Fuse? If not, I'm going to move on to the fan out, which is the data fuse almost oh, there is a question. David, is one model more risky than the other? Go ahead.
Yeah, I'm just curious, when you think about this fuse approach, is it more risky to potentially translate that through the browser, through like a session or a cookie, where that session may expire or get lost or corrupt versus doing it through the database asynchronously?
Anything that's going to go over the open internet is going to be inherently more risky than if you manage it within your services and systems in your own environment. So this would work. And for some things where the risk of failure is low, it may be acceptable. But replicating the cart, in this case, if you've got the cart here and you replicate it across, how long does it take to move that kind of data into the checkout system? You can manage and be certain that that comes through without having to risk going over the open internet.
Just to add some more context, this is where the actual design itself and understanding the personas and actual patterns are important. So the reason we show this example here is if the likelihood of failure is at the browser, remember from our math of risk times probability, it's probability times impact. The impact is really small because the failure is only for that one user, that one browser. Every other customer is potentially not impacted. Now, so this would be a case where you might have a mobile user or a user on a poor connection where that may be the case. Or you can design on the front end a way to pick that back up. So so some patterns will lend themselves more towards let's do this in the browser versus others you might want to do it through replication on the back end. So the other part is how soon do I need in that next service need that data? And so how quickly can you get the data from service A to service B? So, but in general, if you look at just the entire architecture, usually it's a lower risk in the browser. And that's the quicker way to do it because you've only impacted potentially one customer. Your blast radius is small. But there's a lot of complexity when you get down to A and B. You actually have to redesign the architecture. There's a lot more design to do a split of add to cart and checkout.
All right,
Doug.
Let's look at fan out. This is the inverse. So you've got a service that is calling two other services and fanning out. So the response time is dependent upon either which of these services are slower. The correction for that in many cases is what we've already discussed. It's not necessarily a service in series, but the solution is the same. Put in a message bus between those services so that the communication is no longer dependent. You can get the answer from service B independent upon when you get the answer from service C. Making a non-blocking request. Services that need to call each other should always communicate asynchronously, and that's the reason we've got the buses in place. You can also apply the libraries in this case, just like we have in the other areas where you can eliminate the cross-network call and serve all of everything that's needed within the environment the service is native to. Same thing here. You can have your calls out to the browser. There's no server-side integration, and integrate the responses at the client. Database fan out is exactly the same. Don't allow a service to call multiple data stores with distinct data sets unless you've got sharded data that requires you to look in two different places to be able to pull all the data necessary for the query that you've got. Separating the service and separating the data is another element that we always look for, that you have an independent data store for each service that is served only to that service, and it guarantees fault isolation all the way through. Likewise, if you got data from both databases necessary, the services are able to provide that directly to the browser and recombine it back at the browser. We've also looked in here where you've got a write service and a read service, and asynchronous replication between the data sides to make sure that everything rolls through correctly. That is certainly key when you're reading a whole lot more than you're writing, if you've got a series of queries that are looking to data that's been written once. The other thing you can do is shard your data by customer. So you've got shard 1 has D1 plus 2, and you've got the same data on reads over for customer shard N to be able to look at the data. That's a relatively easy thing to do across some systems and services based on the nature of the customer data you have. Any questions on that before we jump into the mesh?
I do want to just make one comment on the mesh. You'll hear the term service mesh a lot. What we're referring to here is only implementing a mesh in the wrong way. So usually when you build a mesh architecture, this is what you want to make sure you do not implement.
right here. It's akin to spaghetti code. Each service calls each other service, and the math behind it is that the lowest available service in this entire body, in this case, we've got 6, raised to the exponent of the number of services times the number of services. And what you're looking at there is the number of connections between service SC connects to 5 other different services. So you do the math and you've got an exponent. So if you've got a service, the lowest service availability is 99.9%. You've got 6 services, that's 99.99 or 0.9999. Raised to the 36th power, you've got 99.64% just based on the mesh. And it gets even worse at 99.5 or 99.9. When you've got 3 nines, you're actually running around 96.5%. Philip, did you answer David's question? Or is that
Yeah,
yours?
that was
Oh,
the one.
sorry, it's not
That
yours.
was the older one. I just made a comment.
Good.
Yeah, this drawing, these are synchronous calls, not asynchronous.
Correct. Never deploy services in a mesh simply because it makes a mess. It's a mesh mess. There's some better ways to tackle this though. In fact, if you look at the way we've got this in here, you can easily spot that we've got calls in series. If one service calls another, and that service calls another, and that service calls another, you've built in automatically the anti-pattern for a service in series. You also have got data service as data fuses or service fuses because each of these can call service D, and then you can easily see that there's multiple individual elements in that for that. We've also got fan out, data fuse, and a data fan out. So this is generally bad, which is exactly what Philip was getting at. So what is not a mesh? Services that are deployed separately or in some level of orchestration like Kubernetes don't really count as this. The key is that the services do not communicate with each other. They've got to have isolation in between. Appropriately then, if you've got to have the communication between them, do it asynchronously through a bus and don't block or stall execution while you're waiting for a response. We're able to apply libraries here as well. If you've got 6 different services, service A would need to have libraries that would cover the services SB through SF. And you can read that as well as I can. Each of these libraries has to be available to cover the needs for each of those services, and you eliminate the service mesh all the way through it. Philip, anything else before we jump into the patterns? Okay.
Nope.
Sidecar. This is a deployable service that helps to handle some reusable components within the environment. You see the obvious potential uses for monitoring. If you've got some specific monitoring you want to do on the service, you can have a sidecar service that's specifically designed to interrogate the service and deliver monitoring directly. So the service itself is not recoded to manage the monitoring. You've got a sidecar that'll do it for you. So observability is an easy thing to pick up. Rate limiting, some level of circuit breaker. If you've got a follow-on service that may or may not be available, you can use a sidecar service to query that service on a regular basis and make sure that when you make a call, it's able to succeed. So if I've got an anti-pattern if I have a sidecar that's going to too many services, I can actually build out a mesh, as you can see right here. So don't use them as proxies to all other services, make them distinct. Next pattern we'll walk through is the ambassador pattern. This could be looked at as a primary API. So you've got a remote service where you've got an end user that's coming through the gateway, an ambassador service that is built on top of a legacy application, almost like a facade that manages the communications in and out of the legacy environment for remote services or end users. Very, very popular and easy to manage and very useful and when you're trying to retrofit or maintain an old monolith that doesn't have the ability or a need to be modified. Has anyone used either the sidecar or the ambassador patterns in your environments? David says no.
In some cases, you maybe know this and not know it. A lot of times people just do this with their load balancers and are taking particular endpoints and doing it. So a lot of times we recommend use those capabilities, don't have to build that.
Stephen, you willing to share how you've used it as an API gateway?
Sure. Yeah. The ambassador service basically in front of legacy services that had really custom APIs, so not RESTful APIs, but using an internal kind of custom serialization format. So the ambassador service kind of plasters over the internal services to give the end user a clean RESTful API.
Good. I'll raise one that I did years and years ago, and I won't tell you how many years ago, but when I tell you that we were using a universe database, it may give you an idea. Exceedingly legacy systems. We actually had to encapsulate it. It was an old, on a VAX system, so it was using the VAX operating system. We encapsulated a Unix environment and then used a Linux service to interrogate it. We kept that little piece of software, critical for a medical device manufacturer, kept it alive for another 12 years. I didn't want to, but I didn't have any option because we couldn't find anybody who could modify the code. It was that old. This one you probably have been either aware of or you used yourself. The strangler pattern is probably one of the most popular ones because it's the best method to try and break down a monolith. You build a proxy on top of a monolithic software package. That proxy is just capturing those things that are necessary and need to be routed to the new service. The service then manages those parts of the transaction process or parts of the application process. Anything that is still in the legacy part of the monolith would route there. Over time, the monolith gets physically smaller. You may not actually delete the code, but you stop referring to the code that's in the monolith within the software or from outside. Multiple services then continue to bounce through the proxy and manage their requests independently of anything in the monolith. Once everything within the monolith has been removed, and this last one may be the remaining piece of the monolith, that it's no longer cost effective or cost beneficial to try and break it any smaller, you can eliminate the proxy altogether, and then you've got a service-based application. Do a proxy, but we advise against doing a proxy on top of a facade. Build all of that activity into the proxy itself. You don't need this unnecessary facade on the front. Anyone have familiarity with Strangler? Is it something you've used to break apart legacy monoliths in your environments? David, you willing to share?
Yeah, we had a service that we called it car scans, but basically it had a set of vehicle information that we needed to break out of our monolithic. So what we started to do was to isolate data being fed through that service and start to build out a corresponding service and database on the side and start to funnel, traffic and data to that new service over time and isolate the existing monolithic service and start to deprecate, less data going to it. First it was traffic going to it, then it was getting rid of the reads that we had to that and start moving it over. And that was an effective approach for what we were doing for our use case.
Good. Still some more work. You got more things to strangle out of the monolith? You have other things you're going to do?
There may be a couple more, but that was the core one that was causing us a lot of performance, latency, and resource utilization from a CPU and memory perspective for us. So we took the high value, high risk ones first.
Thanks. Next pattern we'll look at is the command and query responsibility segregation, CQRS. You got a number of write commands coming from a service directly to a master database. Reads and writes split between services in the database. So you build in a series of copies of read database clones and route all of your reads and queries through the service to those clones instead of to the master. And all of that is eventually consistent over asynchronous replication. We've talked about that in a number of different places, but this is a very easy way to reduce the overall load on that master database by splitting the reads.
And a lot of you that are in AWS are probably taking advantage of native, the RDS capabilities that are doing this for you today versus trying to build this yourself.
Next is a bulkhead pattern where you're trying to isolate individual faults. Very important to keep the failures within their own swim lane. Why? You eliminate the ability for a failure of one to impact the others, to reduce the blast radius all the way across. So how do we do that? Edge network, generally you don't worry about isolating that. It's a lot more cost prohibitive, but it's easier at the firewall level. And we've got the option and recommendation to have multiple firewalls, multiple routers all the way through, load balancers as well. They can bottleneck and fail. Each swim lane now has its own firewall so that they're independent of one another. The next level down with web servers, app servers, and storage, always isolate those. The top of the rack switches, so whatever's serving that individual rack and the compute and storage necessary for the functions and features that are in it. This is at the infrastructure level, but the same principles would do apply across the services as well. I talked about the circuit breaker pattern where a service is calling to a circuit breaker service. This could be a sidecar that is calling to another service with a request. That's the normal operations flow. What happens if it breaks? I have a request that goes to the circuit breaker. The circuit breaker is unable to contact service B, so I've got an abnormal operation, and I flag that I've got a timeout or a failure altogether, and I send back, rather than a failure or a non-response, I send back the fact that I have an error, and it knows, then service A it knows that it has to query again after a period of time, just a retry after a certain period of time. Monitors for times or repeated failures. The nice thing is it fails gracefully, so you don't have an abend within the service A. Aggregator pattern, we've got a few different ones we're going to walk through. You've got responses for the end user that are necessary from both service B and service C. Service A is aggregating all of that information on behalf of the end user. In an API implementation then, I've got browsers, mobile, and third-party services all coming in through an API. That one API is serving multiple needs. Some benefits to that: it's easy to understand, relatively simple to walk through, but you all are also inheriting at least a couple different anti-patterns. Which ones can you guys see and identify? Fan out. Yep. I've got fan out from the public API to these three services. And I've also got a service fuse from the browser and three different points going into the public API. So I can put in a backend for a front end where the browser has a browser BFF that's referring to those services. The mobile and the third party, we still have both fan out and fuse in this environment. I've resolved it at the browser level, at the user level. So each one of them is going directly to an individual service, but I still have the fan out problems all the way through it. So if I have a browser, I can have an individual service back end for a front end for each of those, and that resolves the fuse at the service level. I still, to some degree, I have individual service calls, so these wouldn't be considered a fan out because each of these are distinct. Any comments or thoughts on the BFF?
Yeah, are any of you implementing BFFs today? Any show of hands? A lot of folks, yep. Are you doing GraphQL? Do you mind sharing why you're doing it? And it's very common. There are reasons why you would do it. Stephen?
Yeah, sorry, I was typing there. Yeah, there's a mobile BFF, and it does use GraphQL.
Yeah. So that's just the risk. Just make sure that whatever benefits you get, typically it's time to market. You need to get some features out there. You're taking on trying to increase usage of the platform, whatever benefits you get there, while although you increase the likelihood of failure if not implemented properly. But there might be reasons you might do it. Just be aware of the risks of why you would do that.
Gotcha. Yeah.
Next pattern we'll hit is the dumb pipe contract. And it is a contract. The individual services and the pipe itself has a contract of what's necessary to manage communication into and out of the contract. So the pipe is dumb. It just takes the information. The services, both the publishing and the subscribing services, know what they're looking for and follow the contract necessary to make the pipe itself very simple to implement. So there's a four-way to look at it, where you've got producers and you've got consumers that are distinct. If you've got a smart producer and a dumb consumer, you need to have a pipe that's smart enough to manage to give the consumer what they're going to need. On the other side, if you've got a smart consuming service and a dumb producer, you need to have a genius consumer so that they're able to manage what they're looking for. What we're looking for is a smart producer and a smart consumer that allows us to leverage a dumb pipe, where the pipe now can be used for any service as long as they follow the contract necessary. The services themselves are wise enough to be able to interpret and deliver the information and pull the information that they need. Gateway pattern is very similar to the ambassador we were looking at. In fact, the ambassador can be used as a gateway service, where the remote services or the users all come through a common entry point for any of the services and data that they require for the application needs that they have. All right, Philip, I'm doing all right on time. I'm trying to leave us some time to get to the ones at the end. Event sourcing is one of the ones that I wanted to walk through in a little more detail. These are a little more complicated. Some of the ones we've walked through are relatively straightforward, relatively easy to design, but the event sourcing is a little bit different. Consider I've got information coming from a service. It's writing into the data. There's some elements of the data that need to be available for me immediately to manage the transactions that I'm doing for my customer. We take a propagator then with the data that needs to be filtered in based on individual services or elements. One is updating customer data, one is updating sales data, perhaps, into a dumb pipe, and the services manage the subscriptions and take care of the data rights necessary based on the events that were captured in the data for service A. At the same time, or maybe on a regular temporal basis, we'll take those events, summarize them, and do updates and creates or appends only into a data lake for a long-term storage or queries and some of the analysis that comes from it. Once the summarizer has performed all the work, it deletes those events that were necessary from this area so that we know that they don't need to be processed again. So we're managing the immediately necessary events in real time, asynchronous calls, but the response is immediate. And the summarizer into our backend data systems for analysis are on a different timeline, maybe 2 or 3 or 4 times an hour. Claim check pattern is another one that's not difficult to understand. If you have a claim on you don't take your coat with you to the table when you go to a fancy restaurant. You get a claim check. You come back to the valet, hand them your ticket, and they bring you your coat. This is exactly the same thing in practice. We publish to a dumb bus. The element here is if you've got a data package that's more than a megabyte, don't send it to the bus. Send the data package that needs to be processed to a secondary data store that's just for that purpose, and send a trigger to the services that there's something waiting for them in the checking area, in the valet area. So they've got to go to that area to get the coat. Each service will then independently read based on the trigger that came through from the bus. They'll pick up the data out of the data store, process the data, and they are removed by a cleanup service, once again, 2 or 3, 4 times a day. So you know everything has been processed all the way through. That avoids having very large data sources inside your bus, and it's just the trigger that there's something to be processed and managed. All right, Philip, we did it. We made it to the saga.
Very good.
All right, I'm going to hand this off to you if you want to tackle it and go through it.
So saga is when you really need to basically do a workflow. The idea here is that Service A needs to then pass some information to service B, which then needs to pass something to service N. And this is very common. So Saga in this case is in series. It's a sequence because you can't have these things run in order. A has to occur before B, B has to occur before the next one, and so on. So that's what is Saga. There's going to be two versions of that. And let's go ahead and show those. So ideally you want to do, if you can, you want to do async in this case. So you'll have a publish subscribe, and then you have A is only responsible for write operations and actually updates and deletes for A. Same with B, calling database B. And so you've got your publish and subscribe in between. So in this case, you probably need an event-driven architecture here. You're probably going to use something that's a managed service, probably from AWS, perhaps something from another third party. So let's go to the next one. And the reason we go back, we sometimes call this an anti-pattern just because there's so many points of failure here. Even though you've got asynchronous here, look at all the components that could potentially fail here. And so that's the concern here is, how do I manage all these potential failure points? Even though things are asynchronous, it's very difficult here to manage these, particularly if in this one too, when you need to, let's say you get service A, you go into service B and then service N. If, for example, service B fails, you have to roll back. And so you not only have to roll back B, you have to roll back any writes you've done to A. And so choreographer is you're trying to basically choreograph these throughout your architecture. And let's go to the next one here. I think the last one is orchestrator here, where you're trying to really manage this whole thing. So by the time you've done this, you've actually built a workflow engine in this case here. And so this is if you get to this point, you'll definitely want to have an architect and think through this orchestrator pattern so that you can do this in the right way. But again, your challenge is when you need to unwind and roll back any transactions. So I'm going to put a note here in the webinar of a platform you might want to look at if you get to this situation. Before I do that, are any of you in the Saga situation now? Do you need to do a workflow where you need to have either what's in your previous service was a two-phase commit, or a multi-step where I need to make sure if something fails somewhere in a chain, I need to roll it back? Any questions? Is anybody on the webinar in that situation today? All right, I'm not seeing any
Doesn't look
ones,
like it.
but yeah.
Good.
And this is more common when you are in the B2B space. We've also seen this sometimes in e-commerce space when you're trying to replace that series, any part of the chain of add to cart or cart all the way to checkout. That's a common one where if you need to roll something back, that you can roll it back successfully. So, and I'll put a note in here for that one. All right, Doug, I'll pass it back to you.
All right. The last piece we wanted to walk through is Brewer's CAP theorem. Not sure if you guys are familiar with it. CAP is consistency, availability, and partitions, the partition tolerance. The elements here are simply that distributed systems that are in multiple network locations can only support two of those three. You cannot get all three of them. Consistency, all the nodes are going to see the same data at the same time, all of them. The availability is that you're going to get a response from all locations, guaranteed response, or you've got some level of partition tolerance where the system is going to continue to run even though some of the messages, some of the consistency of the data sources may not be there. It's going to eventually be consistent, but at any moment in time, they're not exactly the same. With a database, you can have only two of those, either high availability plus a network partition, or you can have high consistency and a network partition. You can't have high availability and high consistency in a distributed system at the same time. Questions or thoughts, comments? All right. Well, gang, we are reaching the end. Next time, 2 weeks from today, availability and the scalability cube. And then at the end of February, we'll look through architectural principles across the board. In the mid part of March, monitoring and operations. Thanks again for being with us. Go out to our YouTube channel and subscribe. We love having you here with us. Thanks for being here. Have a great weekend.